let's go over A. So in our system, we have 3 energy levels to start things off. We have energy is 0 for the ground state, energy is equal to epsilon, and energy is equal to 2 epsilon. So for part A, we're saying that we're operating in the canonical ensemble, meaning that this is how we define our partition function. That's what that information tells us. And we're saying that our particle can only be in each of these 3 states. So if I look at the canonical partition function for a single particle, how many states do I have? So how many summations should I have? 3. So I just should have, in this case, Q is going to be equal to the summation over all the states I of the energy of that state scaled by the Boltzmann factor. So that means my single particle partition function is going to be e to the negative beta 0 plus e to the negative beta epsilon, e to the negative beta 2 epsilon. And of course, this is just 1. That's question A. So part B. What I'm asking for part B is what is the degeneracy of the 3 epsilon energy level if n equals 3. So now what this means in normal human speak is what are the number of ways that I can create a system that contains 3 particles that have a total combined energy of 3 epsilon. Right, so this is going to be our combinatorial statistics. So first, let's start off with indistinguishable particles. Give me one configuration of the system where we have a total energy of 3 epsilon.
Epsilon.
There we go. So I'll write this as 1, 1, 1. Energy level 0, epsilon. Oh, sorry, no, this is going to be, this would be epsilon, 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 right? Okay. That's what I did in my notes there for some reason. What's another configuration?
2, 1, 0.
Right, so we have 0, epsilon, 2, epsilon. Are there any other configurations of the system? Does that have energy of 3 epsilon?
0, 0, 3.
We're contained to only the first 3 energy levels for this particular problem. So in that case, this is the only 2 ways that we can have the system with indistinguishable particles. Okay. Has anyone worked it out on their own? How many can you have with distinguishable particles? Does anyone have an answer? Okay, work it out on your own.
3, 7.
The right answer has been said, but I don't know, I'm not going to say which one it is. So this is how I set it up here. It's just a matter of keeping track. So I have particles 1, 2, 3, and then counting down, so particles here. I wrote which energy level they're in, and hopefully they should all add up to 3 epsilon. So do we have any questions on writing the partition function? right, who's got, what are their numbers? What do you guys get? How many different configurations of the system are there?
7.
We have 1 vote for 7. Who else has 7?
I got 7 as well.
All right, I got 7 also. So in this case, I had energy level 1, 1, 1, and then it's basically 6 combinations of the other ones. 0, 1, 2, 0, 2, 1, 1, 2, 0, 2, 1, 0. Those should all add up to 3. Okay, part C. The question is asking, for a single particle system, what is the probability of the particle having energy epsilon at infinite temperature? So this is saying basically the probability of energy epsilon if T goes to infinity or beta goes to 0. Intuitively, what is the right answer? No mathematics.
1/3.
What'd you say?
1/3.
1/3. Why do we know that it's 1/3 intuitively?
The energy states at t equal infinity, all 3 will have the same probability.
Exactly. The only way that you can ever not violate the second law of thermodynamics is that as you increase the temperature, you must always be increasing your density of states. You can never decrease the probability of the system being in a particular configuration. Meaning that at infinite temperature, all configurations are equally likely, meaning that you've reached a maximum entropy configuration. But let's say imagine, and the reason why I choose epsilon for this question and not 2 epsilon, is people may mistakenly assume that at infinite temperature, the system is in the highest energy state. This is not appropriate because it would basically reduce the number of states and it would reduce the entropy. And that's one of the main things that we'll be talking about today, is how entropy relates to probability and the density of states. So mathematically, right, probability of epsilon is equal to e to the minus beta epsilon over the partition function, which we've already written, is 1 plus epsilon minus beta epsilon plus epsilon minus beta 2 epsilon, right? But as beta goes to 0, or the temperature goes to infinity, this goes to 1, this goes to 1, this goes to 1, and equals to 1 over 3. Are we good? Now D is where it gets a little bit more challenging. So in part D, I want you to derive a continuous function for, yes, Scarlett, question.
On board C, why is capital Q is equal to small q?
So it's only one particle.
Okay.
So the whole collection of particles partition function is the same thing as a single particle partition function. But in the case of part, let's see, D, we're deriving the single particle partition function, but in this case, the number of states is unconstrained. The energy of the system can, in essence, go all the way to infinity. Now, the approximation that we're making is that the energy levels, E0, E epsilon, 2 epsilon, are very, very small, that we can approximate them as a continuous function. So what we're looking for is the single particle partition function, where we're summing up over all the states I want you to evaluate this function here to get, well, I've given you the answer here, right? But your result should look like this here. Now this is where things get a little bit more complicated, but you can see that the general workflow that we're doing is the same procedure that we've done for all the other StatNext systems. We define a simplified system, we calculate its properties, and then now we're generalizing it to an arbitrarily sized system to get its macroscopic properties. Right, so this is the same procedure that we're doing, except ours is a little bit less physical than, let's say, particle in a box, which is really where we get the ideal gas law that we talked about on Monday. Okay, evaluate this function. So I'll give you a few minutes to work through that. And please do raise your hand, because this is the simplified version of an exam question that you'll have on StatMech. But since I'm giving it to you in class, it's obviously going to be more challenging on the real exam. It's not going to be exactly the same question. So it's important that you understand how to do it. To kickstart everyone in the right, get them going in the right direction. What's going to be our first step to accomplish this here?
To convert this into an integral.
Exactly. So the key piece of information is saying that these energy levels are very close together, so we can approximate the summation as an integral. Now this is not going to be the case, well, sorry, it is the case for kinetic energy. It is not going to be the case for vibrational energy. So in fact, the model that we choose to model the vibrational energy of a diatomic gas, which we'll talk about on Friday, that's going to be the harmonic oscillator. Now the harmonic oscillator was chosen because it has a convergent infinite summation, right? So again, these are modeling approximations to the real physics. So in this case here, right, we're instead going to be integrating from state 0, right, because that's going to be our base energy level, but even if it wasn't, we're saying the states are pretty close together, all the way to infinity, okay? The next step is we have e to the minus beta multiplied by some representation of the energy, and we integrate this over some independent variable. Can someone tell me how to fill this in? How should I write this? Give me an example of how I could write it. How do I generalize a mathematical description of this physical process here?
So it would be beta epsilon d epsilon.
No, not quite. So how can I write the energy of an arbitrary state of a single particle?
Is there n epsilon d n?
Yeah, you could do that. We could do n epsilon d n. Right, because we're counting up all of the different energy levels. And so at any n times epsilon tells us what that particular energy level is. So now, it should give you a mathematical problem. So what is the integral of an exponential function? So in this case here, the single particle partition function is equal to what? How do we integrate this?
Plus 1 all divided by
So it should be, is it minus 1 over n epsilon, right?
in beta.
Beta epsilon.
Oh, beta, sorry, beta epsilon, right. Evaluated from 0, oh, I'll get this right eventually, e to the minus beta, epsilon, evaluated from 0 to infinity, right?
Won't it be plus one into the exponential?
No.
No.
I think I didn't box that, right? Let's see.
Oh, it's exponential.
It's exponential, yeah, no.
Yeah, okay. So then I plug in infinity, so this is equal to minus 1 over beta epsilon multiplied by e to the minus infinity minus e to the 0, right? This goes to 0, this goes to 1, so negative 1 times through by here gives me the partition function is equal to 1 over beta epsilon. This is the same exact procedure we used for particle in box. Okay, the last step, part E. So now that we have the single particle partition function, right, and you'll notice, just let's do a really quick deconstruction of this particular problem, because this was a real exam problem that I used. Part A, right, obviously it's the start of the problem, so it only depends on the problem statement. Part B, does B depend on A? To get you points on the exam.
No.
No. Okay. Does C depend on A or B?
Yes.
Kind of.
Kind of on A.
Kind of on A, but also kind of just on physical concepts. If you know there's only 3 energy states, and you know the concept that as temperature goes to infinity, all states are equally probable, you actually don't need A to solve C. Having the correct answer in A does, of course, help. Okay, D. D does depend a little bit on A, but that's more so just understanding the concept. Really, all the challenge on part C is this translation here, is how do you generalize that energy level. Okay, next one, E. Does E depend on anything else? Doesn't actually depend on D. I gave you the answer on D, right? So these are the types of ways I like to write the questions, because then I don't have to worry about propagating uncertainty or propagating mistakes throughout the whole problem, right? So in this case here, when you're looking at this exam, don't neglect part B, C, D, E, or whatever the case is, because you don't know how to start the problem. You may be surprised. So in sort of getting the most points that you can out of the system, do not just forget about what's going on, right? All these questions are more or less trying to be written independently so that you have as much opportunity to succeed. All right, so what we're asking for here is, what is the internal energy? In this case, this is equal to minus the natural log of the partition function, the partial derivative of the natural log of the partition function with respect to beta. So, how do I write the partition function for a collection of particles based on a single particle partition function?
Multiply all of them.
Yep. So how should I write this?
Q1, Q2, Q3.
How can I write this more generally for n number of particles?
Plus pi of Qi.
Right, this is the way that we scale up a single particle partition function to a collection of indistinguishable particles within the partition function. Then if we substitute in our single particle partition function, we have 1 over beta epsilon raised to the power n multiplied by 1 over the number of particles factorial. So all we need to do is strictly just evaluate that integral. So go ahead and do that. Who's got it? What'd you get?
N over beta.
Yes. The internal energy is N over beta, or this is also equal to N kVT. Looks very similar to what we saw for the particle in a box example. So just really quickly, if we were to write the natural log of Q out in a more convenient form to hopefully make this sort of an obvious conclusion here. This term right here, so we have negative natural log of n factorial, and then we also have, in this case here, minus n natural log of beta epsilon. Actually, no, we don't need this here. So this would be beta minus n natural log of epsilon here, right? Now the reason why I did this is because I know trivially off the top of my head that the derivative of a natural log is just the radical function 1 over beta. So this is not a function of the temperature, this is not a function of temperature, only this one is here, right? The negative cancels out here. I take the derivative of this, it's just the reciprocal. So that gives me n over beta, or n kVt. Now, we all have the hindsight of basically 150 years of advancements in chemistry and physics. And I still don't particularly much enjoy the concept of a partition function. So hopefully we can empathize a little bit with Boltzmann in trying to convince people that this is the appropriate way to think about how particles behave in terms of atomic theory. But this is really the same procedure that we would have taken for a classical particle with kinetic energies. And that's how Maxwell-Boltzmann distribution was derived, right? The most probable configuration of the system as a function of temperature, as a function of mass. But in the case of the Maxwell-Boltzmann distribution, this was all performed where the energy levels here were different. They were in essence 1/2 mv squared, right? That's the procedure that we did. We didn't do it from a classical, we used particle in a box, but the particle in a box is the same analogy. Questions about the procedure for what we just did? Okay. Maybe it doesn't make 100% intuitive sense, but at least the procedure kind of should be a little bit more clear after that example. Now for an exam, I would give you necessarily a different energy function, right? We could do it in a different ensemble, but in general, all you need to do is generalize how we can write the energy for an unbound system, and then we can calculate its properties through the partition function. Now, the other type of question that I will ask relates to entropy. So in the last class, we derived an expression for the entropy in the canonical ensemble that looks like this. Okay. Now, so,
Minus
no, there's no minus. Hopefully I didn't have a mistake in my notes. But I think I did have a mistake when I wrote the Boltzmann equation last class, and I did have a minus. It should not have a minus. Now, how we derived this expression here was basically relying on classical thermodynamics to manipulate the internal energy and substitute in the partition function into that expression. So we didn't go through the math too much, but effectively that's the conceptual procedure that we took to get to this point here. Now, we can rewrite this, and if people have questions, we can go through the procedure. Maybe I'll just reserve it for a homework problem, actually, to show that these two equations are equivalent. We can rewrite this with this expression here. such that the entropy of the system is actually the probability of, summing up over all the states, the probability times by the natural log of the probability. So effectively, if you substitute in this expression, substitute this expression into those two terms, you can show that they're equivalent. This is a very famous equation. It is called the Gibbs entropy equation. Now this is related, and you can simplify this to get the Boltzmann entropy equation. And we may get there, I don't know if we will. So, let's take the example that we just worked on. Let's say we have a system with 3 equally probable states. Right, meaning that the energy of those 3 states are the same. So if we look at the probability, right, we have the same number here divided by 3, which means we have a 1/3 probability of being in any of those particular states. So that means if we apply the Gibbs entropy equation, that means our entropy is equal to minus KB multiplied by 1/3 natural log of 1/3 plus 1/3 natural log of 1/3 plus 1/3 natural log of 1/3. Which is going to be equal to minus KB times by 3 natural log, oh sorry, there's 1/3, this is just 1. And this is approximately equal to 1.1 kV. That would be the entropy of this particular system. Now let's say we have a system with 10 equally probable states. Okay? We'll again apply the Gibbs entropy equation. S is equal to, in this case, negative the Boltzmann factor. In this case, I'll just simplify it down a little bit. It'll be 10 times by 1/10 natural log of 1/10. Right, we'll have, this is 1, 2, 3. We'll do this for 10 different times in this circumstance here. In this case, this cancels with that. And we get the entropy is equal to minus KB natural log of 1/10. And this is approximately equal to
2.3.
Oh, you're very good. 2.3 KB. I don't know my logs that well. Very impressive. So, this is where we get the interpretation of entropy from a statistical mechanics perspective, that as you increase the number of states, you are increasing the total entropy of the system. Now, for this particular example, we were operating not really necessarily in the canonical ensemble, but something new called the microcanonical ensemble. Because in this simplified system, the explanation was that each of these states are at the same energy level. So if all of the states are at the same energy level and have the same probability, that means we are no longer, right, in an NV beta system, right? We are now actually in what we call the microcanonical ensemble, which is NVE. Constant number of particles, constant volume, and constant energy. So if we exist in the microcanonical ensemble, and how we could write that, sort of from a physical perspective, is that we have a box. Inside of this box, we have a particular volume, we have a particular number of particles, they have a particular volume, after they have a particular energy. Now what happens here is that the number of particles cannot change. It's impermeable, nothing goes in, nothing goes out. That means the volume is constant. There is no PV expansion work that goes on. And then lastly, it is adiabatic, and the heat in and out is zero. So this is a completely isolated system, and we call this the microcanonical ensemble. So the probability of any system being in some energy level EI, right, is effectively then just going to be equal to 1 over the microcanonical partition function. Because all of the energies are constant, meaning that they are all equally probable configurations. Now you'll note, right, that this capital omega, this is the same nomenclature that we used for the degeneracy of a collection of particles. That's because the microcanonical ensemble is the degeneracy of a particular energy level of the canonical ensemble. Now, if we substitute in, and hopefully it's I can kind of skip over the math with respect to time, but it's fairly intuitive conclusion. If we are to substitute in our probability for the microcanonical ensemble into the Gibbs entropy equation, where entropy is equal to here, what we'll effectively be doing is we'll be summing up basically the number of different states to get to the microcanonical partition function, right? That's the number of configurations within the system. The probability here is going to be 1 over the microcanonical partition function. Same here, the natural log, again, 1 over the microcanonical partition function. So if we substitute this all in together, we'll effectively get minus KB multiplied by the number of configurations in the system, multiplied by 1 over the number of configurations in the system, multiply the natural log of that probability function. These two cancel out, and if I flip this up to get it into the numerator, we now have derived the Boltzmann entropy equation. Now this is the famous equation that's on Boltzmann's headstone. The only substitution is that instead of omega, it's W. But I think it's a fairly trivial nomenclature substitution. Right, and this is really the basis of our understanding. Now this equation here was generalized by Gibbs, I don't know, maybe 40 years later, 50 years later? I don't exactly know the timeline. I believe in the 1920s, 30s-ish period is when Gibbs was generalizing that. So the Gibbs entropy equation is by far the more generalizable. This one only applies to the microcanonical ensemble, whereas the Gibbs applies to basically all the systems. But this is really where we get the concept here that the number of states in the system corresponds to the entropy itself. Now this is the ensemble that we'll use a lot of times if you want to ever work in a lattice-based model. So in a lattice model, what we can more or less do, and there's a lot of models like Flory-Huggins theory. Has everyone heard of that one? Flory-Huggins theory is a lattice-based model for mixing of two liquids. It's particularly useful for polymers. So effectively in a lattice model, what we'll be doing is we can fill in particles in different positions, and based on the number of particles and the size of your grid, you can calculate the total number of configurations of the system. So this gives us a direct way to calculate the entropy. Now the only downside is that the real world doesn't behave to lattice grid positions, and so it's a little bit more complicated to actually apply this. But this is where the key concept comes in for that particular relationship. Now, the last thing that we'll talk about before we depart for the day we can relate the microcanonical partition function to macroscopic thermodynamic variables exactly the same way that we did for the for the canonical ensemble. In this case, we expand entropy with respect to, in this case here, U, V, and N. So again, we'll just recap what that looks like. Hopefully this should be familiar. S, D, U, actually, V and N. D, U plus S, D, V at constant. This would be U and N. D, V plus S, D, N, constant U and V, D, N. Substitute in our expression for the microcanonical partition function. Now through thermodynamic identities, ds du at constant v, anyone want to tell me what that is? Remember off the top of your head?
Temperature.
Yeah, 1 over temperature. ds dv at constant u and n. This is pressure over temperature, actually. This is du dv plus this one here, ds dn at constant u and v. This is a form of the chemical potential. This is actually minus g over t dn. So what we can do is we can come up with expressions now. If we were to go through the mathematics of it all, we can show that the reciprocal of the temperature is equal to that pressure over temperature is equal to and that. All right. So this is one of the main reasons why I kind of like the Sandler book for StatMech, is because it gets us out of the weeds sort of as soon as possible when it comes to deriving these functions. So we can directly go, as soon as we kind of get a gateway in to a macroscopic property from the partition function, then we can very quickly just manipulate it using our tricks from macroscopic thermodynamics. So again, we should be viewing the partition function as kind of like a state variable of the system. And so all we're doing is instead, in classical, we're used to Gibbs, Helmholtz, internal energy, entropy, enthalpy, all these different concepts. But now with StatMech, we're kind of just adding on the partition function, but we can still manipulate it and substitute it more or less as if it were a state variable of the state thermodynamic function. So it's an abstract concept, but we do have ways to calculate it. The meaning of the partition function isn't all that significant, but when we manipulate it, that's where it tells us the thermodynamic variables. Okay, submit your homework, please, and see you in class on Friday.